let's take a look at what we can consider a linear relationship and what would be a non-linear relationship. To get us started, here's a whole bunch of different equations and graphs. And so when we're looking at this, we're trying to decide if something is linear, which would be a straight line, or if something is non-linear, which would have a curve. So I think a few of these are pretty simple to look at right away. So for example, this picture right here, we can see that we have this curve, in which case this would be non-linear. Same with over here. In this picture, we see this nice curve, therefore non-linear. But if we don't have a picture, then how can we figure out if something is linear or non-linear? Well, the way to decide is actually by looking at your exponents. Anything that has an exponent 1, your equation, all your exponents are just a 1, it means that it is a linear function. But if your exponents are not 1, so 2, 3, 4, and so on, or maybe even a variable, x, y, z, then it would be nonlinear. So let's take a look at each one of these. We have y equals 3x plus 7. So I can see my y doesn't have an exponent, so it would be a 1. And my x doesn't have an exponent, so it would be a 1. So this would be considered to be linear. Okay, how about over here? So we have 2 to the x minus 3. Right away, we can see this x minus 3, that is not an exponent of 1, right? That's an exponent of x minus 3, therefore nonlinear. Okay, how about this next one? As we look, we can see that we have 12 minus 3x plus 2y plus x plus y. All these variables don't have an exponent on it, so they would all be 1s, which means that this is linear. If we graphed it, it would be a line. And then this last one here, we have an x cubed. See how we have an exponent of 3? 3 is definitely bigger than 1, so this would be non-linear. So as long as your equations just have exponents of 1 on them, then it's linear, but anything else would be non-linear. So what we're going to actually start talking about then in this chapter 4 is all about quadratic relations. And the first thing that we want to do is just look at whether or not we have a linear or non-linear relation. So if you're able to, just draw a quick sketch of what you think the graph would look like on the following scenarios, and then I'll show you what it really would look like. Okay, so let's say you had a candle, okay, and you lit it, and then you walked away, okay? So what would be the graph that would represent the height of the candle as it's being burned? So if you think of it, you light your candle and then it's burning. What is happening to the height of that candle as it burns? Pause it right here to try to draw your graph and then come back to see the solution. Okay, so hopefully you're back. So a possible solution would look like this, where you have some kind of a height and then it would burn steadily right till it had absolutely no end left. So that could be a possible solution. Try another one. What could be a graph? Oh, actually, before we go to this, as we can see, is linear. It's a nice line. Candle would burn, and as it burns, the height would decrease, and we get a nice line. So that would be linear. Okay, how about if you threw a ball off of a bridge? What would that look like? Okay, so pause it here, draw your graph, then come back for the answer. Okay, possible solutions to what that could look like is the ball, if you threw it out sideways, it could go this way. Maybe that's what you're thinking of. In which case, of course, then this is linear, or sorry, non-linear. We have this this curve that's happening. Or you could think of, if you just didn't kind of really throw it, if you just dropped it and it went straight down, and if that's what you were thinking, then that would be linear. So the graph could really depend on what you decided to draw, either or. Okay, Jeremy the snail is trying to get to the creek. Today, he is 100 feet away. At the beginning of every day, Jeremy determines his distance to the creek and then crawls half the distance. Draw a graph to represent Jeremy's distance from the creek. So, for example, he was 100 meters today, then tomorrow he would be 50 meters away, then the next day he would be 25 meters away, then he would be 12.5 meters away, and so on. So pause the video here and come back to see your solution. All right, let's take a look, see how Jeremy did. This is what it would look like. Look at this. So he was at 100, then 50, and then he was at 25, and then 12.5, then 6.25, and then on and on and on. And we get this lovely curve. So this is non-linear. All right. Draw a graph to represent the height of a toy rocket that's launched from the ground. Okay, so a toy rocket launched from the ground. Again, pause it here, draw your graph, and then come back and see the solution. Okay, so hopefully you're back. So this is what it would look like. The toy rocket would take off, it would gather some height, it would hit a maximum height, and then it would come right back down. So we can see this produces a lovely curve. This is non-linear. It would go up and then it would come back down over time. How about a Ferris wheel? What would a Ferris wheel look like? So think of this. You get on the Ferris wheel at the bottom and then it goes around and around and around. What would the graph look like that represents the height of the person as it's going around on this Ferris wheel? Again, pause the video here and then come back and see your final answer. All right, so the possible solution that this could look like could be this. So you get on, you go up to the top, then you go to the bottom, then you're up to the top, then you're at the bottom, and so on. And of course, we can see that this is non-linear. All right, a solar light uses sun's energy to charge batteries. The batteries are then used to power electronic devices. Draw the graph to represent the amount of power stored in a solar battery of a solar light from midnight one night until midnight the next night, assuming that it's a sunny day. So can you draw the graph that represents the amount of power that's going to be stored in that solar battery of the solar light? Pause it here, come on back and see what could be an answer. All right. So this one, we want to think about it. So the bottom would represent time, and then it would be power. And then, so let's say that it's going to start from midnight one night until midnight the next night. So when it's like midnight till, I don't know, 6 a.m., let's say, 1, 2, 3, 4, 5, 6. So let this be 6 a.m. We're not going to get any power because there's no sunlight out. And then from 6 till probably maybe 10 o'clock at night, so 6 a.m., let's say to 10 p.m., we could look at there's an increase. But then once it gets dark again, then we get the decrease. So we get kind of this, what we call piecewise graphs, right? It's kind of in pieces because different things would be happening at different time. This parts of it are linear, like this part here and this part here and this part here, all independent of each other, are linear. But if you take a look at it as a whole graph, then we would have to say it's non-linear because it's kind of in pieces. Yeah, so as we look at this, we can see that these different pieces are definitely linear, but combined all together, then it doesn't really make a graph that's well, it's non-linear only because from beginning to end, it isn't one straight line, but it is kind of linear and as it is in pieces. Okay, so a few important things to remember. An independent variable always goes along your x-axis, and for us, as we talk about different situations, time is always independent. So if you're ever looking at like time, hours, minutes, seconds, that's always going to be on your x-axis, and then your dependent variable will go along your y-axis. If you have a bunch of points and they suggest a curve, then it's nonlinear. And any graph that ends up with a curve is considered to be nonlinear. And that's about it.